Hi, my name is SLC from SingaporeStudent.com. Today is 24th of April 2012. I'm going to continue with the topic today, which is how to draw the trend of the first ionization energy of elements from hydrogen to calcium. The way we draw the graph today is similar like the previous two explanation before. There are three factors affecting the amount of ionization energy of the elements. The ionization energy is, to put it simply, is the amount of energy needed to remove one electron from the atom. So, if it is difficult to remove electron from the atom, then the first IE will be high. If it is easy for, if it requires a small amount of energy, then the first IE will be low. Now, we are going to do the similar process like yesterday. We are going to calculate effective nuclear charge and the number of shell and electronic configuration. In this case, we need the electronic configuration will affect the amount of first IE, and we are going to see that later. The electronic configuration, some of the electronic configuration of these elements are stable, so in that case it's going to be more difficult for you to remove the electron. Then the first IE also will be higher. So we can start now. The first thing we do is simply fill up all the elements, right? By now I think you can quickly do that because it's quite easy. Nitrogen, oxygen, chlorine, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. And we fill up the number of protons of each element. Very simple. It's in the sequence 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The inner electron for hydrogen and helium are of course 0. From lithium to neon is of course 2 because they are on the second period, which means the 2 electron on the first shell is considered inner electron. Very simple. From sodium to argon, of course you have 10 electron, 2 on the first shell and 8 on the second shell. For potassium and calcium, you're going to have 18 electron on the inside. Effective nuclear charge, we simply minus away the number of protons with the inner electrons, so similar like the previous trend. So 1, 2, 3, 4, 5, 6, 7, 8. From sodium to argon, same, minus away. It will be increasing from 1 to 8. Potassium and calcium increase also from 1 to 2. So that's the effective nuclear charge. The number of shells also very simple. Hydrogen and helium have 1 shell. From lithium all the way to neon have 2 shells. Sodium all the way until argon have 3 shells. From potassium and calcium is of course the fourth shell, right? Very simple. We are going to draw the trend here. Effective nuclear charge. The higher the effective nuclear charge, the more difficult it is to remove the electron, so the first IE will be higher. So this red arrow represents increasing IE. So from hydrogen to helium will be increasing. From lithium all the way until neon will be increasing. So remember, this red arrow represents increasing. From sodium all the way until argon, it will be increasing also. Potassium and calcium also. How about the number of shell? Intuitively, you know, very simple. The more shell you have, the farther away the electron from the nucleus, then it's going to be easier. So this green arrow represents a drop, a decrease, and the decrease is very significant because the position is the change in position is quite far. So this green arrow represents a significant decrease or a big decrease in the ionization, in the first ionization energy. Now I mentioned about this electronic configuration. We cannot put the whole electronic configuration on these small boxes. We just put the last electron, the electronic configuration of the last electron of hydrogen. So 1s1, 1s2. Lithium is of course 2s1, 2s2, 2p1, 2p2, 2p3, and so on. 2p4, 2p5, 2p6 for neon. For sodium, starting from 3s, so 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, and for argon is of course 3p6. So 4s1 and 4s2. As I mentioned, some of these electronic configuration are stable. How are we going to deduce which electronic configuration are stable? Very simple. Remember, your teacher mentioned that if the p orbital is full or half full, then it will be stable. Same thing for s orbital. So all the s2 orbital will be stable. So we mark with orange color. 3s2 and 4s2 also. For p orbital, if it is half full and full, that means p3 and p6 is going to be stable. So 2p3 and 2p6, 3p3 and 3p6 are stable. How does this stability affect our graph? If it is stable, then the IE tend to be higher. So then it will be, the ionization energy will be slightly dropping. So the effect is not so significant, but still you can see it. So this orange arrow represents a slight decrease in the first ionization energy. Now we are ready to draw. Right? You can copy our answer here on this one, our pattern, right? You can copy your answer into our pattern. You can, of course, remember I mentioned you can download this from my website. The answer is this one. I give the answer also on the website. Pretend you didn't see this, right? So what we do is we draw the green one first. The green mark, the one that you have a significant decrease in the first ionization energy. And remember, for small atoms, the ionization energy is high, so we start from a very high one. So from helium to lithium, there will be a significant decrease. From neon to sodium, there will be a significant decrease. It's supposed to be more significant. From argon to potassium, also there will be a significant decrease. Then the next one, we draw the effect of effective nuclear charge. So as I mentioned, this red arrow represents a gradual increase in the first IE. So we are going to draw from hydrogen to helium. It will be increasing. Now in the case of from lithium to neon, you're going to draw the red arrow, but it will stop until it will be a bit jagged. Stop until barium, so like this, and from boron to nitrogen, from oxygen to neon. Same method applies here. Sodium and magnesium, from aluminium all the way until phosphorus, and from sulfur to argon, and potassium to calcium. What's the reason? Why must we cut it into this portion? Simply because you're going to draw the effect of this electronic configuration. As I mentioned, this orange arrow here represents a decrease. So there will be a slight decrease from beryllium to boron. Also slight decrease from nitrogen to oxygen. There will be a slight decrease also from helium to lithium. So from helium to lithium, there are two things that affect. Is because it decreased because of the number of shell, and also it decreased because of the less stable electronic configuration. So the same thing applies here from sodium to neon. So this one also from magnesium to aluminium, from phosphorus to sulfur, and also here from argon to potassium. So we see all these three factors are affecting first ionization energy simultaneously, That's why I want you to draw. I want you to fill up the table. This is my answer. This is how I draw. Right? This thing is posted on the website also in singaporestudent.com. The correct one is of course from the computer generated graph like this. So this is the first IE, so it looks quite similar. Of course, you can't expect it to be 100% correct, but for sketching purpose, is this correct? Right? I hope this is useful for you. If you have still have difficulty, still can contact me. You can also come to my trial lesson every Saturday. You can call me at 90885633. Is the basically you need to check my website and contact me. Thank you. Bye.